Welcome back for our second chapter in our pre-calculus saga, which will deal or discuss the topic of functions and everything foundational to what's to come in your later mathematical explorations. We're going to go back and revisit the topic of domain to ensure that we have a firm grasp on what that entails. So today we're going to be learning that the domain of a function is a set of all possible inputs, and the range is a set of all possible outputs, so I can determine in writing the constraints on the domain of all functions. I'll know I've got it when given a description of a function that represents a situation, can determine reasonable domain and range. In nearly every physical phenomenon, we observe that one quantity depends on another. For example, your height depends on your age. The temperature depends on the date. The cost of mailing a package depends on its weight, and so on and so forth. Functions are mathematical building blocks that are used to describe this dependence of one quantity on another. So I'd like for you to think of a real-life function. Think critically. Don't just Google it. It will allow you to develop a much deeper grasp of the knowledge. All right, so we have a doozy of vocabulary for this particular slide. We can say that a function f is a rule, a symbol that represents an arbitrary number in the domain of a function f is called, put down my pen, an independent variable. The independent variable you as the user have ownership over. The symbol that represents a number in the range of f is called a dependent variable. Thus, if we write y equals f of x, we internalize x to be the independent variable and f of x, which is really, or y, the dependent variable if we want to think of it graphically. This symbol, f of x, is read as I had just said it, f of x, and is called the function notation. Set of all values of the independent variable x that result in real number values for y. So what we're saying here is the x values that when we substitute into the function produce an output is known as the domain of the function. The range of f is the set of all possible values of f of x as x varies throughout the domain. In essence, the domain of the function is the set of all inputs for the function, and the range, the set of all outputs. Functions can take inputs from many variables. What we mean by that is there are numerable, I can't think of the word right now. There are many different inputs that we can substitute into a function, but they must uniquely produce the same output, unique to that function. Probably doing these way too late. In layman's terms, a function associates exactly one output to each input. What are some functions that have certain restrictions regarding their domain? Why do these particular functions have restrictions? We've talked about this before, so this is kind of jogging your memory. Share that with the class. Okay. First up, before we get to our checkpoint, my domain and range red markers. The example of a polynomial, we can use x to the third power minus 3x squared plus 4x. And some constraints on that domain is there are none. We love polynomials because polynomials are considered continuous functions from negative infinity all the way to positive infinity on the x-axis and on the y-axis. They're perfect. However, rational functions, such as one like this, our biggest domain constraint exists in the denominator because it is not allowed to be 0. And as far as radical functions, like square root functions or fourth root functions or sixth root functions, let's say we have something like this, these have constraints because the final value within the radical cannot be negative. Because if it is negative, we'll have an imaginary number, and imaginary numbers cannot be graphed on our real number Cartesian plane. So work out these functions on a piece of paper and identify the domain of the following expressions. You can identify that domain using interval notation, right, using your brackets or your parentheses, depending on if things are enclosed or not enclosed. And you can also use set notation, where you basically use inequalities to describe what is happening. In the definition of a function, the independent variable x plays the role of a placeholder. To evaluate a function f at a number, you simply need to substitute the number for the placeholder. Substitute the number for a placeholder. A piecewise defined function is a function that is defined over a specific interval, as we can see here in checkpoint 2. I'll leave the first half for you, but in the second half, we would consider c of x a piecewise function because it is behaving differently depending on the context of its interval. The interval or the inputs reside between 0 and 2. The function is behaving constantly as the value 39. If the input is greater than 2, then the function is behaving in a linear fashion as 39 plus 15 times the quantity x minus 2. So remember, a piecewise function is a function that is defined over, let me clarify that is defined by different formulas over different parts of its domain. A little bit more clear. As we round out our lesson for today, we have 4 different ways to represent a function, right? We have verbal, algebraic, visual, I like to use graphical, and numerical using a table of values. Okay. If we're able to connect an algebraic formula to a graphical representation, and how does that appear numerically, and how can we take that in context? That is our comprehensive understanding of a function. And so in checkpoint 3, I ask you to do all of the above aside from producing a graphical representation, because this is a gnarly graph. But given this function for an astronaut's weight above the surface of the Earth, what is her weight when she is 100 miles above the Earth? Construct a table of values. What can you conclude from the table? And then you'll find the net change in the astronaut's weight from ground level to a height of 500 miles. And that brings us to our enhancement opportunities, where we'll pick up together in class.